Myself Dr. P. Vijayakumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to see one of the application of continuous random variable is uniform random variable. So, uniform random variable, we will see the definition of uniform random variable, and we will see the distribution and density function of uniform random variable, and we will see the applications of uniform random variable. And also we are going to learn another learning outcome at the end of this session. That learning outcome is we will apply the concept of uniform random variable for solving the real-time problems. So, coming to the definition of uniform random variable, a random variable is said to be uniform random variable if it follows the density function something like this. If the density function is something like this, fx of x is equal to 1 by b minus a less than x less than b, and it is equal to 0, otherwise we call it as uniform random variable. And when it comes to plot, the plot will be something like this. Any plot which is similar to this plot, we can assume the random variable as a uniform random variable. And the distribution function for uniform random variable can be computed as mathematically. We know that the distribution function is integration of density function. We know the distribution function is integration of density function. Using this formula, when we compute the distribution function 1 by b minus a integrate du a to x, you will get the distribution function something like this. Okay. Next, coming to the applications of uniform random variable. So, generally uniform random variables are applied in almost so many applications. We will see some few applications. So, let us see in the communication systems how it is applied. So, in the communication systems for random signal generation in digital communication, that follows a uniform distribution. Similarly, random phase generation also follows a uniform distribution, generally over the phase range 0 to 2 pi. And for modeling time offsets, random delays also, we use the concept of random variable. And also in signal processing also, we use the uniform random variable concept. So, white noise approximation over a finite intervals, tethering in ADC and DAC to reduce the quantization error, random test signal generation. And also in computer science algorithms also we use this uniform random variable for hashing functions, load balancing, randomized algorithms, random sampling and shuffling. We use this uniform random variable concepts. And also in control systems we use for random input signals for system identification, testing the system robustness using uniform distribution disturbances, and electronic and embedded systems. So, like this there are so many applications: statistics, probability, cryptography and security key generation, and also in gaming applications. So, real time in gaming applications we use this uniform random variable, random movement and object placement, texture generation and procedural content, fair random outcomes, dice, card, loot systems. So, all these we apply the concept of uniform random variable. So, let us see the problems related to the uniform random variable. Problem is given something like this: x is a uniform random variable distributed over the limits a comma b is equal to 0 comma 5. We need to compute the probability that the probability of x less than 2, the probability of x less than 2. So, from the given data we need to find the density function first. We know the density function is fx of x is equal to 1 by b minus a over the limit 0 less than x less than 5. So, this is the density function. Now, we need to compute the probability one by one. Probability of x less than 2 means probability of x less than 2, and the range of function defined, it is the density function is defined over the range fx of x is equal to 1 by 5 over the limit 0 less than x less than 5. So, x less than 2 means 0 to 2 fx of x dx, fx of x dx, fx of x is 1 by 5, doing the integration we will get 2 by 5. Similarly, x greater than 4 to infinity will get 1 by 5, and if the probability of x lying between 1 to 3, we will get 2 by 5. Okay. Let us take one real time example for uniform random variable. Starting at 5 a.m. for every half an hour, there is a flight from San Francisco airport to the Los Angeles airport. Suppose none of these planes is completely sold out and they have always room for the passengers, and a person wants to fly to Los Angeles, arrives at the airport at a random time between 8:45 to 9:45. Now we need to compute the probability he or she waits at most 10 minutes. At most 10 minutes, that means maximum 10 minutes. So for every half an hour there is a flight. So the flights starts from 5 o'clock. From 5 o'clock there is a flight, 5:30 goes on 9:30, 10, like that the flights will be arriving up for every half an hour. For every half an hour we can catch a flight between San Francisco and Los Angeles. Now a person is arrived over the time interval 8:45 to 9:45. 8:45 to 9:45. Now what is the probability that he will wait for at most 10 minutes? At most 10 minutes when he arrive over the time interval 8:45 to 9:45. So before going to the actual problem, we need to write the uniform distribution function. So for every half an hour, let us take for hour 0 to 60, the distribution density function is defined. Now he will wait at most 10 minutes. When he arrives at 8:50 to 9 a.m., when he arrives at 8:50 to 9 a.m., up to 9 a.m. he need to stay in the airport to catch the flight. So when he arrives over this time interval, then he need to wait at most 10 minutes, maximum 10 minutes. Another scenario also can happen over a time period. When he arrives over the interval 9:20 to 9:30, to catch the 9:30 flight, he need to wait at most 10 minutes. So two cases are possible. So the two cases are now 8:50 to 9, 9:20 to 9:35. So 9:30 to 9:30. So applying those variables, calculating the density function, we will get the probability 1/3. In a similar manner, the second scenario is the probability that he or she waits at least 15 minutes. At least 15 minutes means they need to arrive over the time interval 8:45 to 9. He can catch 9 a.m. flight. Other chance is 9:15 to 30. So 0 to 15, 30 to 45. Applying the concept of uniform distribution function and computing the value, we will get 1/2. This is one practical example, okay. And another practical example is a point is chosen in a line segment. A line segment is there, 0 to 5. A point is chosen randomly between 2.5 to 4. 2.5 to 4, a point is chosen. Okay, what is the probability that a point lies between 2.5 to 4? Given it is a uniform distribution function. So the line segment range is from 1/b minus a, 1/5 minus 0, 1/5. The line segment range is from 0 to 5. The probability that a randomly chosen point comes between 2.5 to 4. So 2.5 to 4. 2.5 to 4 comes under the range of 0 to 5. So we can use 1/5 dx. We will get 0.3. Next one. Number of personal computers sold daily at Computer World is uniformly distributed with a minimum of 200 computers and maximum of 5,000 computers. What is the probability that the daily sale will fall between 2,500 to 3,000 computers? So firstly, the maximum value B is 5,000, the minimum value is 2,000. Now the density function is 1/b minus a, 1/3000 over the limits 2,000 less than x less than 5,000. So firstly we developed the density function for the given function. Now we need to compute the what is the probability that the daily sales will fall between 2,500 to 3000 PCs. So 2500 to 3000 falls under the given range itself. So simply substituting and integrating with the given density function, we will get 1 by 6 chance. Next, what is the probability that the sales is at least 4000 PCs? At least means minimum 4000, maximum can be up to maximum. So 4000 to maximum value is 5000, 1 by 3000 dx, we will get 1 by 3. Now what is the probability that exactly the sales is 2500? So this we cannot calculate. Okay, there is always a range for continuous random variable, exact calculation is not possible. Similarly, an x is a uniformly distributed random variable with the density function given as -1 to 3. That means a is equal to -1, b is equal to 3. So fx of x is equal to 1 by b minus a, 1 by 4, -1 less than x less than 3. He is asking us to calculate probability of x less than 0. Probability of x less than 0 is 1 minus probability of x greater than or equal to 0. So x greater than or equal to 0 means 1 minus 0 to 3. The limits are from the limits you can use here 1 by 4 dx, we will get 1 by 4. This is one more practical example related to the real time application. You know that your college bus arrives at your boarding point sometime uniformly distributed over the interval 8 to 8:20. That means assume x is the minutes, x is a random variable which indicates the minutes, 1 by 20 minus 0, 0 less than x less than 20. Okay, x indicates the bus arrives in a minutes. Now what is the probability that you have to wait longer than 5 minutes? When you will wait more than 5 minutes, when you arrive over the time 8:05 to 8:20. You will wait more than 5 minutes, because if you arrive after 8:05, here 5 minutes, 5 to 5 minutes, 10 minutes, 15, 20 minutes you need to wait. So 5 to 20, 3 by 4 is the probability. The probability that you have to wait at least 5 minutes if the bus has not yet arrived at 8:10. So for at least 5 minutes means minimum 5 minutes. So when he comes over the time interval 8:10 to 8:15, this is the chance 1 by 4. So here what we have seen is the application which is related to uniform random variable. So firstly what we need to do is we need to develop the density function. Nextly we need to identify the ranges of the probability, whether this range falls over the defined density function range or not. So based on that we need to apply this formula. So 10 to 15, 1 by 20 dx. So 1 by 20, 15 minus 10, 1 by 4. So based on the range, we need to see whether it comes under this range or not. If the given data comes under this density function defined range, and we can calculate simply by doing the integration. Okay. So in this session what we have seen is we have seen the definition of uniform random variable, and we have defined the uniform random variable, we defined the density function of uniform random variable, we defined the distribution function of the random variable. Any random variable which follows this density function, we can assume it as a uniform random variable. And also we have seen some real time applications where we apply the concept of uniform random variable, and we have seen few problems related to the practical or real time environment uniform random variable problems. So in the next session what we will see is we will see the problems related to the exponential random variable. So we will define what is the exponential random variable, and also we will define the density function of exponential random variable, we define the distribution function, and we will see some applications. We will see some applications related to exponential random variable, and we will see the problems related to the real time problems. Okay. Thank you.